Jiapeng Zhang from USC, and he'll talk to us about streaming lower bounds for needle problems.
Thanks, Andoni, for introduction. Today, I will talk about streaming lower bounds for the needle problem. Okay, so this talk based on two joint works. One is with joint work with Shachar Lovett, and the other one is a joint work with Qian and Shuo Wang. Okay, so in this talk, I will cover 4 parts. At first, I will introduce what is the needle problem, and then I will talk about some lower bounds, and then I will also give 2 proofs. So because we have 2 joint works, so basically 2 proofs. Okay, so let's get started with the needle problem. This problem is a pretty simple problem. I mean, the statement is very simple. So we consider 2 distributions. One is just a uniform distribution over a large domain. Yeah, by the way, if you have any question, feel free to stop me. Okay, so the first one is a uniform distribution. So the second one is just, we first sample a needle. We sample element, we call it a needle in this distribution from this domain, sorry. Sample X, and then we sample many samples. So such that it equals to X with probability P and uniformly otherwise. So there are 2 distributions, and the goal is going to distinguish them. Okay, so the question is that given bounded memory, so how many samples do we need to distinguish these 2 distributions? That is the question. I hope it's clear. Yeah, if I have any questions, feel free to ask. Okay, so we're good? Sure. Okay, so let me first.
What should I think of PS?
P is just a parameter, something between constant and the square root n. Yeah, if this is much smaller than square root n, then probably you're really hard. 1 divided by square root, sorry. Yeah. Okay, so let's discuss some simple algorithms so that everybody can have a sense about the problem. So the first setting is that, okay, without any restriction about space, you can use whatever you want over the space. So then we have a most straightforward algorithm, just restore all of the samples. Right? So just put everything in the memory and then just count the most frequent element. So of course, this will be the needle if you have enough samples. By simple probabilistic calculation, you will know that whenever you have more than 1 divided by P samples, then you can find the needle with high probability. And yeah, and the space, this is a straightforward algorithm. It costs log n divided by P space, because for each sample you need log n space, and so you have 1 divided by P samples. Okay, so this is the first setting. The second setting is that I have a really small space. So really small means you have probably log n, all the log n space. So then another straightforward algorithm is probably just, okay, we just take all of the samples and remove them and only keep the most recent 2 samples. Whenever you see 2 identical elements in the, 2 consecutive identical elements, then you say, okay, so this is probably the needle. So in this thing, if you do a calculation, you know that you need 1 divided by P square samples. With this amount of samples, then with good probability, you can find 2 consecutive identical elements. And in this setting, we only use all the log n space, right? So in both settings. And so for general space, actually you can extend a general trade-off between these 2 algorithms. So whenever we have S space, so basically we just store most recent roughly S number of samples. According to your calculation, then you need roughly T is divided by log n divided by S times P square samples. So in all of these trade-offs, so the trade-off here is that whenever you have S space, then your sample is roughly log n divided by P times S times P space. Okay, so the question is that, yeah.
So there is an algorithm also that you.
All right, so what about this algorithm that you focus on whether this needle is the element 1, and you'll read at most like like 1 over P elements, like log n over P, and if the needle is not that one, you move to the next one and next one.
But you don't know the needle.
Yeah, that's why you are iterating over all possible choices of needle. What does that give you? So there is an algorithm that uses order log n space. You assume the needle is the first one.
Yes.
You need log n over p samples to decide whether that's correct
Yes,
or not.
but how about if this is not the needle?
Then you move to the next element.
Yeah. So, okay, so this is a good algorithm, but I'm not sure what is the time space for this one. We can do a probabilistic calculation. Yeah, but my main focus today is that I want to show this is almost tight.
Okay.
Yeah. So you can do whatever smart algorithm, but I want to show no matter how smart you are, this is roughly the tight one.
Got it.
Okay,
Perfect.
actually there is a non-trivial algorithm, so it's able to remove the log n factors here. So yeah, so the best algorithm, the optimal algorithm known today is that the trade-off is t is roughly 1 divided by sp squared. Okay. So yeah, actually, so my next question is whether this is tight. Okay, so basically we prove this is tight. So this is our result. So we showed that whenever you want to distinguish these distributions with constant probability, then you need 1 divided by s times p squared samples. And also we can generate it for any L pass algorithms, multi-pass streaming algorithms. So basically you just multiply another L by here. Okay, so that's it so far. Okay. Okay, so why we started this question? Yeah, actually, I was not sure why should we study this question when even we proved this result. Yeah, because this is a byproduct of our communication complexity result. So after we have this result, we somebody asked David, asking whether this is important. Okay, so they told David told us, okay, so basically you give some applications, so it's somehow important. Okay, so one of the applications is that in the frequency estimation setting. So I think a frequency estimation is a really important problem in streaming algorithms. So basically you want to estimate the frequency moment of a data stream. Okay, so but I won't spend too much time on here. So as a corollary, so we can show that for if you want to estimate frequency moments, so you need omega n to the 1 divided 1 minus 2k space. Yeah, and so for the previous best known result was given by Andoni, McGregor, and Penny Graphy is the n to the 1 minus 2.5 divided by k space.
I was to ask, so throughout this talk, all your bounds that you state, you're implicitly making the assumption that p is at least 1 over root n. Is that correct?
Yes.
So I guess that probably answers Sepper's question as well, because 1 over p squared is better than n over p, which is what you.
Yeah. Okay, sure. Okay. So yeah, so we improved this here. Yeah, and then also this is the random order setting of the frequency estimation. So all of the samples comes from a random order, not the adversarial order. Okay, so then we are talking about how could we prove this lower bound. Okay, so in order to prove this lower bound, actually, so yeah, as I said, this is a byproduct of our communication complexity results. So we spend a lot of time to study disjointness problem in the communication complexity. So the disjoint problem is also can be stated simply. So basically, you have a k party. Each person is k players. Each person has a set Si. And so we promise you that either of these SIs, all of the sets are disjoint, or there is a unique intersection. Unique intersection means there is one common element which belongs to all of the sets, and for every 2 pairs, the intersections of these these sets is exactly x. So by removing the common element, so all of the rest are disjoint. Okay, so the communication complexity problem is that we want to distinguish these two cases. And so this is a very important result from communication complexity is that the randomized communication complexity is roughly the summation of this size I divided by k. And this is also pretty tight pretty tight to a simple upper bound algorithm. So let's go back to this problem. So if you want to design an algorithm, so what is the most intuitive way to construct the algorithm? To construct the communication protocol to distinguish these two cases?
For the smallest SI?
Yeah. So the smallest SI just going to say, okay, so this is my set. The player I which has the set Si with the smallest size, and going to tell everybody else, okay, so this is my set Si. So the cost is roughly the length, the size of Si times log n, because each Si has is an element of n. So basically, this is this. Okay, so this is the most straightforward. Sorry. Okay, so this is the straightforward upper bound algorithm. So if all of these SIs are almost the same size, so basically they'll reach the lower bound by up to a log factor.
So are you in the Blackboard model or message passing?
Okay, so it's just everybody can. I think it's broadcast model. Everybody can talk to everybody else. Yeah, and the lower bound is a really strong lower bound because these are really strong model. Yeah. Okay. So how it connects to the needle problem? Okay, let me give you a really simple explanation, and I think this is very intuitive. Okay, so let's imagine that's in a data streaming setting. So because we have probability p to get a needle, so in expectation there are roughly p times t needles, right? Okay, and so let's consider a simple case. Okay, so let me just try to just partition the data, the streaming samples. So we have t samples. We just cut by cut into p times t parts. So each part has roughly 1 divided by p samples. So basically, the first 1 divided by p samples. This is the second 1 divided by p samples, and blah blah blah. I'm just going to cut them and reshape them in this way. Looks like a matrix. And each row has 1 divided by p samples. Let me tell you a very simple. Let's study with a very simple case. Is that I promise you that each row has exactly 1 needle. So then how? Okay, so this is a very simple case, right? So then how can it be connected to the streaming needle problem? So basically, whenever we have this communication complexity lower bound, how could we convert this lower bounds into the streaming lower bound? So basically, the idea is going to use the communication protocol to simulate the streaming algorithm, right? So then we can make a connections between them. Okay, so how could we use this communication complexity to simulate any algorithm A? So basically, we have 2 settings. One is the streaming algorithm. So now we want to simulate it by communication protocol. I think the simulation is pretty simple. So the first player get the set Si, meaning the first row. The first player get the first row, and I'm just going to randomly order it, and simulate this algorithm with the first S element, right? First this element, I simulated this algorithm, and I'm going to pass the memory information at this point, pass this information to the second player. And the second player gets this information, M1, right? And simulate, continue simulation. And all the way to the end, just the last player. So the last player is able to finish off the simulation and output the algorithm A. So basically, I just partition the data and streaming data and send it to each player, and each player simulate one by one. So this is a one-way protocol, very simple communication protocol. And what is the total communication complexity here is k times s. Why k? K is just the number of players, right? K is the number of the players, and each player sends s bits to the next player because s is the space limitation, the space size of the algorithm. So the information of the length of M1 is at most s. So basically, the total communication is k times s. Okay, so the total communication is k times s, and the communication lower bound is from the communication lower bounds. We know that this is at least omega, the summation of this size divided by k, and also the size of omega divided by k. K is the number of players, and recall there are the relationship because we partition the t samples into t divided by p players. So basically, k times p is equal to t. Yeah, and so by combining everything together, we know s times t is equal to 1 divided by p squared. So, but this is a very simple case. The issue is that we are not that lucky to have a symmetric partition such that each part has exactly one needle. So if we record the calculation, whenever we have constant space, whenever we see 1 divided by p squared samples, then with high probability we'll see 2 consecutive needles. So it means it's really hard to partition them equally. So then it means whenever t is much larger than 1 divided by p with high probability, you will see 2 needles in the same part. So this probability is really high. So if you do a probabilistic calculation, we know that with high probability, there are 2 needles with distance 1 divided by p squared times t. So whenever t is much larger than t is much larger than 1 divided by p, then you will see 2 needles are really close to each other. So this partition is really hard. So therefore, we are not able to find such a good nice partition. So this is the main difficulty of this problem. Okay, so any questions so far? You're very fast.
Just to understand, you're saying. So you're saying if we were lucky and the input, like if we fix the partitioning and each player got 1, then it's satisfied us.
Yes, yeah.
But now you want to fix the stream and pick the partitioning afterwards.
Yes, so we have to do asymmetric partition. So symmetric partition, okay, so this is symmetric partition, right? I call it symmetric because each part has exactly 1 divided by p. Yeah, so therefore we have to partition in an asymmetrical way.
Got it.
Yeah. So this is the main difficulty. And and also we also need to change the problem of the communication problem because that was because whenever the difficult so the hardened so we have a lower bound for the communication problem, right? And the harder instance is that all of the set SIs has almost equal size. So that reached the tight lower bound for the communication problem. So yeah, but whenever as we discussed, whenever SI has a different size. So there is one guy which has the smallest set SI can always just broadcast this person's set. So the overall communication complexity is really small. Whenever there exists I which is really tiny, right? So therefore we need an asymmetric version of communication complexity. Yeah, this is the main difficulty. Okay, so what is the asymmetric version of the data of the communication complexity problem? Is that okay? So let's study a more general setting. Yeah, so if all of the set SI has the size at most SI, now I promise you that the sites the k players, again, there are k players, each has a set SI, and I promise you that each set SI has size at most small SI. Now, we want to determine whether they are correct. We want to determine whether they are pairwise disjoint or has a unique intersection. Okay, so let me go back here. Okay, so now for this question, we have another upper bound, is that the sites, we clearly know the upper bound should be at most log n times the smallest SI, right? Because the smallest SI just telling everybody, okay, so my set is really small and this is my set. Okay, so, and we can also prove the lower bound is also omega SI, where SI is the smallest size. But that is not enough. So this is not enough for the asymmetric version, because in the needle problem, we know there are some pair which have constant size whenever t is roughly has 1 divided p squared, for example, right? So there could be some SI which is really tiny. So therefore, we need a really good asymmetric version of disjointedness. So basically, this is proved by Shachar and I. So we proved that the sharp lower bound for the asymmetric version has the following form: is the summation of the I party's communication complexity divided by SI is equal to omega 1. So if you go back to the symmetric version, so all of the SIs has almost the size. So basically, the summation of sigma I is just roughly the size of SI divided by k. Okay, so this is the sharp version of the asymmetric version of disjointedness. And so yeah, as I said, our streaming lower bound is a byproduct of the communication complexity problem. We first have this lower bound, and then we found the application of the streaming. So this I call it the byproduct. So we first have this one. Okay. Any? Yeah. So basically, whenever we have this this one we use this communication. We use the instance of this communication complexity to simulate the original streaming the needle distributions. So therefore, we are able to achieve a tight, almost a tight bound. So basically, we use the hard distribution of this communication protocol to simulate original streaming needle, original needle distributions. So basically, we are able to get T. This lower bound is roughly T is omega 1 divided by SP squared times log n samples. It almost matched the tight bound, except the extra log n factors. And Shachar and I spent a lot of time. We're trying to do a different simulation, different decomposition of the distributions to remove the log n factor. However, we were not able to remove these log n factors under this approach. Okay. Yeah, I'm not going. Okay, any question? Okay, so yeah, but I'm not going to spend too much time about this proof because I want to switch to the second proof, which is the title. It gives the title lower bound without this log n factor by using a different proof. Okay, so the second proof is an information complexity based approach. So this is so the reason this get the tight bound is that we without using the black box reduction to the streaming to the communication complexity problem. So yeah, I call it a white box, but I still call it a white box reduction. So because the idea of proving unique disjointness lower bound is by using one of the nice proof is based on information complexity. But now we are not going to use the communication product to do the reduction, but we going to adapt the information complexity notion directly. So we use the information complexity to prove the lower bound directly without using the reduction from the disjointness. So yeah, this gives a tight bound. Okay, so let me recall the needle distribution. The needle problem is that we want to distinguish these two distributions. So D0 and D0 is the uniform distribution. D1 is the distribution. What time? 18 minutes. 18 minutes. Yeah, it's much faster than I have expected. Yeah, but we have more time to discuss. Okay. So the needle distribution is that there is one needle, and each sample get which equals x with probability p. Okay, so let me introduce another distribution, which is called the local needle distribution. The local needle distribution is just a combination, is something between uniform and needle distribution. Is that I first fix a set S. Okay, so for each first the fixed S, and so for all of those we have T samples, right? We have T samples. So we first fit S is a subset of this T, so fix some locations. So now basically the idea is fixing these locations, and this is the locations. This is the only locations which possibly have the needle. So formally, for each data streaming sample, so if this location is in S, so we output the needle with probability P, and all of the rest are uniformly random.
So just to be clear, when you say S are the only locations where you can have the needle, you could have them in the other locations if he's uniformly picked.
Yes, uniformly. So
okay.
Basically, this is for a fixed S. So basically, we decompose D1 to a combination of DSs. Yeah, this is the idea. Thanks for this question. Yeah.
So technically, this is the same as picking a set of size roughly PS.
Yes.
Fixing the needle, but obviously for the proof,
yes,
it's not
exactly.
going to be different.
Yeah. You guys get the point. So this is my next slide. Okay. So we consider ICs to be roughly 2 times P times S, constants, this size, right? So we first, this set, which is we call it candidate needles, the potential position to be needle. And so in the set S, so roughly half of the needle just by expectation, right? So in expectation, we have P times D needles. So we first sample a set S, which is double the size. And so we call this potential needle. And so half of them are needles. And we can decompose the distribution D1 into the summation of these S's. So we just set like first sample. So we have 2 steps of sampling. First the sample S, then sample needle, real needle. Yeah, candidate of needle and the needle. Okay, so now by using an average argument. So basically, we can show that whenever A is able to distinguish D0 and D1, then it can distinguish D0 and DS for many S. So this is followed by just the average argument, because we can decompose D1 into these forms and by average argument. So for enough DS, for enough S, we can distinguish D0 and D1 very well. And so now the last step, we want to show the information cost. I will define what is the information cost very soon, but just have this in your mind. So the information cost of distinguished DS and D0 is omega 1. So we are first going to restrict the small set S. This is only all the potential needles. So even after this restriction, so you still need omega 1 cost, information cost, to distinguish DS and D0. So this is the proof strategy. Okay, and the last step, we just, because for many DS, so from this step we know A can distinguish many DS and D0, and for each S, such that if A can distinguish, then you have omega 1 cost, and so then the overall cost, we want to argue that is 1 divided by p squared. So because each local S, you have some cost, omega 1, and so have many S, you can distinguish them and combine them together. So this is 1 divided by p squared. This is the proof strategy. Any question?
Okay. Sorry. And the last bullet, sorry, does that last bullet obviously follow from the preceding bullet, or is that part of the thing you're going to prove?
It's not obviously, it follows by the proof. Okay. And also one of the really crucial thing, so this looks straightforward, but one of the really crucial thing is going to how to define the information cost, information complexity. You really need to find a really, really good definition. Otherwise, we cannot prove the tight bound.
Okay, thanks.
Yeah. I think the main difficulty in the previous approach was not succeed is because in previous approach there wasn't such a nice information cost. Yeah. Okay. So let me introduce the information complexity. So okay. So actually we used sorry, I forget to cite the year. It's 2020. So that's the reason I say the previous approach does not have such a nice information cost. This was introduced by 2020. Okay, so this is the information cost by Braverman, Garg, and Udorf. Okay, so this is for one pass streaming algorithms. Okay, so it defines in this way. So MI here I referred to the memory. So MI means the memory status after receiving the X sample, and XK is the case sample. X are samples, and this is the memory status. Okay. So they define it in this way. I'm going to explain the intuition very soon. Okay.
MK minus 1.
Yeah.
So MK minus 1 means the messages up until here.
MK. K is the, so this is, so there are two summations. So the first is the summations from I to T. This is the summation of the samples. And this K just the summation from I to 1 to I.
So I are whom? The players or the times in the stream?
Yeah, both of them times of the receiving the samples.
So M of K, is that M of minus I? What is M of K minus 1?
So K minus 1 is the K minus 1 is the sample. Okay, so sorry, let me add here. Is that you have X1.
Sorry, can I jump in? Isn't MI just the memory state?
Yeah, after the receiving I. Yeah, K minus 1 is the memory state after receiving K minus 1.
Got it.
Yeah.
Okay. Oh, and K minus 1 is less than I.
Yeah, K minus 1 is less than I.
I see. So it's the information, the first K minus 1 player, you condition on that.
Yes.
MI is someone way into the future.
Yeah. MI is something in the future. And XK is something after this status. After K minus 1. So this is condition K minus 1, right? This is the sample next to this one. And this is something in future.
Okay. So the confusing thing is that MI, there are things from MK minus 1 to MI.
Yes.
That will determine, combined with XK, all of them will determine MI. Yes. Okay. And you're ignoring those parts.
Yeah. I just count some of them. Okay. And so this is a really carefully designed thing. So it's not that it's a very elegant design. Okay, so yeah, and so we can show that whenever the samples, as long as the samples are independent, so we can show the information, the upper bound of this information cost is p times s. Okay, so this is not a very trivial thing. If you just by using the very trivial upper bound, say this is something like log n, right? Because this information is upper bounded by the length of xi is log n, and the summation is a t squared. So if by using a trivial upper bound, so you get something t squared. But the crucial thing here is t times s. So yeah, so this is very carefully designed, but the proof is straightforward by information theory calculations. But this design very carefully designed. Okay, I'm not going to show this part. Okay, so yeah, okay, now let me introduce the local information complexity. Okay, local information complexity. This one is really reveals how the intuition. So okay, so let's say we have set S. So the potential potential needles. We fix S, and we define the local information complexity related to S in the following way: is that we have some needles, right? Probably I can draw it here. Okay, let's say this is P1. This is P2. This is PI, for example. This is PI, and this is PI plus 1. Okay, only these positions could be needles. So for each I, if we fix I, okay, if we fix I, so this part is that with summation of OK. So this is probably, this is PK, right? PK, for example. Okay, so we fix the memory states here, condition on the memory state here, and calculate the mutual entropy of this guy. This memory state, calculate the mutual entropy of PK, this PK, mutual entropy of PK, and the mutual entropy of this memory status, the memory here, and the mutual entropy of PK. So the intuition is that, okay, so PI plus 1 could be a needle, right? It's a potentially to be a needle. PI plus 1 potentially to be a needle. In order to detect the needle, so in this location, you must store some needle information about the previous needles. Otherwise, at this moment, you can never know this is a needle, right? This is the potential needle. But in order to detect this needle, in here, you must remember something about the previous needles. You must remember something. So therefore, this is the summation of all things here. We summation all of the needles here. And for each I, we summation all of the needles. And for each needle, we summation all of the previous needles. And what is the mutual entropy of the previous needle and the space before MK? So basically, this is the local information complexity. And this, I think this one is more intuitive, right? So this one is very intuitive. Okay, so yeah, so therefore, we show that a lemma is that if we want to show A distinguish D0 and DS, then this must be omega 1. So you must remember something, omega 1, because if you want to achieve constant distinguishing probability, such as 0.1, then probably overall you need to restore some omega 1 information. Okay, so and the surprising thing is that how could we get a 1 divided by p squared? Actually, this is by a simple calculation, expectation calculation. So how could we show the global information complexity is 1 divided by p squared times the expectation of the local information complexity? Is that it's because for each term right here, what is the probability? Fix I and k. So what is the probability that this probability over random S? Over random S, what is the probability that this term will be chosen to the local information cost? So it is 1 divided by p squared. Why? Because it is chosen to the IS, the local needle information complexity, local complexity information, if and only if both k and I, both I minus 1 or both k minus 1 and I are chosen to be in the set S. So let me go back to here. So both these two things are chosen to be in the set S. So because the set of S is roughly P times T, so each element is in S with the probability 1 divided by P, overall you get 1 divided by P squared. This is how we get the magic number 1 divided by P squared. So just by expectation. So the probability, both of these two are being in S, so 1 divided by P squared, you have 2 atoms. So therefore we get this bridge. So this bridge makes these connections. And so the last step is going, okay. So the last step is going to the information complexity. This is omega 1. So in order to prove this is omega 1, we still use something from communication complexity. So, but we use the communication complexity is going to say each set Si has set almost constant. So if you go back to the original communication complexity problems, is that each party has a set Si. Now we reduce the case that each Si has a size at most constant, omega 1. So yeah, because you fixed the size Si. So each set has a size of omega 1. And the good thing is that now our goal is just going to prove omega 1 communication complexity. Omega 1. So this part becomes easy. So after this partition, I mean this decomposition to ICS, so this part we can use the follows just by previous communication complexity. Okay, so basically by using this idea, we prove this is the tight bound. T is equal to 1 divided by S times P squared. And this can also be extended to the multipath setting. The multipath setting is by using a new notion of multipath information complexity. Yeah. Again, in this notion is only designed for one path. But in order to extend to multipath, we must carefully design and generalize a new version of this information complexity. Yeah, after this new version, I think this the multipath generalization is our main contribution in this work. So we extended to multipath notion, and therefore we can get the multipath tight bound for all P, S, and L. Okay, so this is our main result. Yeah, I'm almost finished. Yeah, thank you.
Quite a bit of time for questions.
Okay. So for the multipath extension, does it also give a lower bound for the multipath version of the coin problem?
Coin problem. So there are many coin problems. It depends on what coin problem you refer.
Oh, I mean the coin problem that was studied in the
by this paper.
BGW paper.
Okay. Yeah. Okay. So. Yeah, probably I can say it for now. Yeah. So we have a discussion with these 3 authors, and they also have their notion of multipath in a very recent unpublished paper, and they used it to prove this tight bound. And we have a discussion about what is the relationship between our multipath and their multipath, and the conclusion is that they're incomparable. Yeah, but I think so. But the thing is that overall, my feeling is that it really depends on the specific problem. So we designed in the same high level way. So we design conditional. We smartly choose something to design to conditional here. So this is both our spirit to design multipath, but there we condition different things because we are studying different problems. So overall, I think it could be dependent on the problem, but we are in the same framework. So basically, condition on something. Different things. Yeah, they have unpublished work.
Any other questions?
Yeah, but there are some follow-up works. So for example, there is a paper by Brown, Wang, and Smith. They used this notion to prove some learning problem lower bounds, and so it was in code 2022. And we checked that with high probability that our notion can be extended to their code paper results. Yeah.
Do you believe that the infrastructure you're using here for the upper and lower bounds can generalize to a problem where there are more than one needles, like a 2 or 3 needle problem?
Yes, this is a really good question. There's another extreme case. Okay, so think about, so there's another question which is 1-to-1 versus 2-to-1. So there are two streamings. One is that all of the elements are distinct. So the other one is that there are many pairs. So each element appears twice, but in a random order. So there are over 2 elements. So this is 1-to-1 versus 2-to-1. And there's also a reduction. So there's also reduction published in Eurogroup 2018. So basically, they show a lower bound for data setting, but they also have an extra log and fact loss. So that is also based on reduction to unique disjointedness, and they also have a log and gap of the upper bound and the lower bound. So what we're trying to do now is okay, so could we use the information complexity to remove the log and factor again? So for that problem. So I think that there are many possibilities here.
Cool. Thank you.
Thanks.
Any other questions?
Do you have any idea on what would be the correct one for p smaller than 1 over square root n?
For p smaller than 1 square root n, I think for data setting, I think we with some chance we cannot recover them. Yeah, with bounded space. Yeah, so when p is much smaller than square root n, if we have an unbounded space, yeah, I don't know. So
for instance, algorithm, let's say fair set gets n over p. So do you have any idea on what should be the correct bound?
So for the so we always for unbounded space, I think probably something you can do is just to remember all of the thing and check what's the most frequent one. And with bounded space, I think this is a really good question. And so in this case, all things this must be very carefully calculated, because in here, for example, everything here just omega-1. But when in a region that the parameters are really tiny, so the dependency over here is really important. What is the accuracy parameter, and so what is the corresponding? There could be some dependency, such like the accuracy is epsilon, and so this is epsilon square. That part even be very carefully calculated in that region. So in here, we just hide everything omega-1, so everything is fine. Yeah.
Thank you.
Yeah.
Any other questions?
That's a question. Suppose I want to distinguish between a heavy needle and a light needle. So I want to distinguish between p and p over 2.
Yes.
I think the communication argument doesn't go through, right? In that case, does the information argument go through?
Okay, so the communication, yeah, we actually. So I'm not going to say the communication does not go through because you say that does not go through because just you apply the original unique disjointedness lower bounds. But you can, such like our unsymmetric version, probably there is a different version of disjointedness, it still make it through. So there are huge number of variants of disjointedness. There might be some of them make it go through. But information complexity approach, I think I agree this is the most straightforward way. I think there's a chance it goes through. Yeah.
That made me think of a different question. What happens if you don't know p? Is there a strategy that's better than just guessing?
If we don't know p, okay. So do you mean upper bound side, right? Or the lower bound side? The lower bound side is still holds.
Let's say we're guaranteed it's big enough, but we don't know what it is.
Okay, so I think it does not affect the algorithm. So the algorithm, we never use the information of p. We just have the information. The idea is just when you store the space until it fulfilled. Whenever it is full, then we just remove the first one. We just that's a window sliding algorithm. We never use the knowledge of p. So the upper bound also goes through, right? Yeah, and the lower bound also goes through because the calculation here, yeah, it only makes this problem harder. So therefore, the lower bound also holds. So the same thing.
Okay.
Any other questions? Let's speaker once more.